All right, let's just get started with the lecture today, which is chapter 4 to cover continuous random variables. Last week we talked about this thing. Put it in the slideshow. Okay. So last week we talked about the discrete random variables and worked through a couple of examples, and also we had homework for chapter 3, which is due this Saturday, and we will also put homework for chapter 4, which is due next Saturday. Yeah, and oh, by the way, I post an announcement on Blackboard that we got a TA. And there will be additional office hour held by the TA. Either you can go in person or you can join, use Zoom meetings. So I think that's a good thing. So you got more resource. When you get problems with homework, with even our code or the course material, you can also go to the TA office hour. Okay, let's just get to today's lecture. Now we move from discrete to continuous probabilities. So last week is discrete random variables, now it's continuous random variables. We're still going to talk about those probability distributions. So for continuous distribution, I mean random variables, the sample space now it's an interval, so it can be any real number between, for example, 1 and 5. So it can be 1.5, 5.2, and any number in this interval. So some examples of this continuous variable would be some measurements of length, of height, and weight, and time. Those kind of things can be measured by a continuous probability distribution. Okay, so again, corresponding to the PMF, which is for the discrete random variables, for those probabilities, we have this PMF, but now we're talking about PDF, which is for the continuous random variable. When we try to get the probability of, say, our random variable equal to C, so we want to look for probability like this, or we want to calculate the probability of our random variable fall within an interval. So that's when we use this PDF. Yeah, so just the same concept. This one is a bit annoying being here. Yeah, so this is just, we always put our random variables on the x-axis, and we plot the probability for each corresponding value. It's a continuous line, but when you pick one single value, like when you see the probability of a random variable x equal to C, then it's always 0. That's for an individual value here. But if you want to get the probability for an interval, then we can get, let's see. Yeah, so when we're trying to find the probability for an interval, we would have to do an integral for this previous line, which is this black line here. In this case, we want to find the probability of x being greater than 0 and less than 1. So that is the area under this curve, but within this 0 to 1 interval. So this is when we're trying to find a probability for an interval, which is nothing but this integral. But intuitively, when we translate into this PDF plot, it's just this area under this curve.
So a PDF is always an interval?
Oh, no, PDF is this fx. See this?
Yeah.
Yeah, so this is fx. But when we try to find the probability of the interval, then this is how we do it.
Okay.
Yeah. I didn't put the formal definition for this PDF, but this fx is actually the PDF.
Oh, so it's just the probability.
Yeah, the probability for each of the values. But this is how we plot it here.
Does it ever go to 0 though? Because it's continuous?
You mean the fx?
Yeah.
Yes. So there are, and also when you look at the probability for a single value, it is 0. Yeah. And actually, this another corresponding definition is called CDF, cumulative distribution function. So this CDF is just this, we always denote it by capital Fx, which equals to the probability of x random variable less or equal to a given value of this small x. So comparing to the discrete cases, now we're taking integrals, where previously we just take the sum for each of the values. So now we're taking integrals. So again, when we do this interval probability, which is kind of similar to this, which is the integral, and the CDF looks like this. So again, on the x-axis is our random variable, and on the y-axis is this capital F being this probability. Okay, so when we plot these two together, they look like this. So this CDF is accumulating all these areas under, like for example, if we want to say the fx being, capital F -2, then that would be the area under here, and then the total area is plotted on this green line. So that's what the CDF is capturing. And I think I have plots here to show you like the. So when you work on probabilities, just like before, when we try to calculate what the probability of something, for example, the probability of x greater than a, which is just the opposite of this capital F definition, the CDF definition. So that's 1 minus FA. And this integral would just be capital FB minus capital FA. And this is a graphical interpretation of this second statement. So for example, our B, so this is trying to calculate x in between 0 and 1. So A equal to 0 and B equal to 1. So we want to get this area in between 0 and 1. What we are doing here is just we get this whole area on the left of 1, and then we minus the whole area on the left of 0. So this area minus this area, we get the area in between. So that's the probability for this interval, which is underneath this curve. So these two things are important. You will use this again and again. Some more terms here. The quantile function is somewhat similar to the sample quantiles when we're solving for this C in this probability of x less or equal to C equal to this Q, this probability equal to Q. So we are trying to find the C when this Q is given. So that is the number such that the area and the curve to the left of it is equal to the quantile that you are interested in. So for example, if you want to find the 95 percentile, which is also the 95 quantile, so we would look for C, which satisfy this condition. So this 0.95 is the quantile quantity, and yeah, and we'll do this in R. You will see this more clearly. How do you find the C with this quantile 0.95? Sorry, I should say this 0.95 being the percentile, and this C being the 95 quantile. It's a bit confusing. So this 0.5 quantile is the median of the distribution. So that's the one in the middle. So that's 0.5 quantile. Well, now we get what is a PDF for continuous variable, and what is a CDF, which is the area on the left of a value. And we covered what is the relationship between quantile and percentile. So this percentile, yeah, I think it just used how to say this. I think it's just a very similar, like use it the same way we say 95 percentile, but when we say quantile, we say 0.95 quantile. So this is kind of the correspondence between these two terms. But anyway, this is just the statement we're trying to figure out. Either we know this 0.95, trying to find this number C, or we know this number C and trying to find what is corresponding probability. So that's what we're going to do in R later after the lecture. Okay, let's go to the distributions. So for discrete cases, we talked about some distribution families, binomial, Bernoulli. Like by given different parameters, you get a different distribution. Those are just a family of distribution. Now for continuous random variable, they also have different distribution families for them. And I only cover some of the important ones. They are uniform distribution, normal, exponential, and beta distributions. Those are the most commonly used ones. Well, there are way more than this. So, but this is what we're going to talk about today. And the same type of R functions we can use for continuous variable. Like we use this D norm for, this is for normality, normal distribution. So this D norm, P norm, Q, and R norm, those we will talk about in the R examples. But let's start with the simplest distribution for continuous variable, which is uniform distribution. So this uniform distribution is, we always denote as this unif with this bracket A and B. A and B just like the two ends of this range that your random variable X would fall in. And the probability that X is of any number between this A and B is equal. So, so this PDF Fx, when A and B is given, the probability of for each of this X being when X within A and B is B minus A, 1 over B minus A. So the probability of X following any number in this interval are equal, and the probability is this. And there is no chance that X will be out of this range A and B. So if X is out of A and B, then the probability is 0. So this is what is talking about in this curly bracket. So the function we use in R is this D unit P unit Q for the PDF and PDF, CDF, and quantile correspondingly. In R unit, that's how to get a random variable following a uniform distribution. Okay, and what is the PDF and CDF for uniform looks like? So just as what the formula is telling you, when it's outside of this A and B, then the probability is 0. So it's just all here, solid line. And when it's within A and B, the probability are equal, and it's equal to 1 over B minus A. So again, when you take the integral for this fx, that means you sum up all the possible values and all the probability for all the possible values of this x, you should always get to 1, because that's the whole sample space for this random variable x. So in this case, like we know the probability of any of the value following A and B is this. So when you try to integral this from 0 to, sorry, I should say from 0 to infinity, because it theoretically can go to infinity for this one. Negative infinity to positive infinity, yeah. So it will always go to 1, because beside this range is all 0, and we only need this area. So that's 1 over B minus A times the length of this area, which is B minus A. Then it goes back to 1. And the CDF, again, it's just a cumulative distribution function. So it's accumulating the area under this line, right? It's adding up the area under this line. So when you plot it out, because all the values are equally likely to happen, so this slope, it just go up with the same slope, with the same rate. So this is the CDF for uniform. And there are more information from Wikipedia, and the picture is adopted from Wikipedia. Okay, so the uniform distribution, that's the simplest for continuous random variable. Now we're going to talk about this, the most commonly used distributions, I would say, in statistics and probability. This is the most common one, normal distribution. And we also sometimes call it a bell curve, because when you plot its PDF, it looks like a bell. So this random variable x is said to have a normal distribution with mean mu and standard deviation sigma if the PDF of x is of this form. So the mu parameter and the sigma parameter just involved in this PDF. Well, this format, this formula may not be that important for you at this moment, but if you, like in the future, you take class Bayesian statistics, you will use this over and over again, and you would have to use the formula. But for now, for this class, maybe this is not so important, but just knowing what the normal distribution is and how do you work with it in R is more important. So yeah, like I said, it's a bell curve. The PDF just look like this. So basically this formula, when you plot it here. So this is being X, sorry, this Y actually should be this Fx when mu and sigma is given, where in this case, the mean is the center being 0. So, well, what about we have different value of the mean mu and the variance sigma square? So this 2 parameter determines a bell curve, right? So I plotted here like for mean being being 0, I have two different values of sigma. So either it's 1 or it's 0.5. So when it's 1, it's more spread out. 0.5, it's kind of narrow, this blue line, because remember this parameter here I put is the standard deviation. A larger standard deviation means more variability, so it's more spread out. And this red line is showing you a different mean value, where the mean is 0.5. If you look at the center of this curve, that's 0.5. So this is just showing you for different parameter sets what the curve looks like.
Can you plot CDFs for this, or is this one?
Well, CDF for normal distribution, oops, I will cover about this later, but CDF for normal distribution is not easy to plot. So we always have a table. I mean, in the old days, we would have to use a table to look for values when we standardize this normal distribution. But now we have R, we can just use R to find the CDF for normal distributed variable. Okay, so yeah, I would have to talk about the standard normal because it's also really important. Well, sometimes you hear people say X follows a standard normal distribution, where it did not tells you what is the mean, what is standard deviation. By default, by definition, a standard normal is that X following this normal with mean 0 and standard deviation being 1. And sometimes, or most often, it's called Z when we refer to a standard normal distributed variable. And if you want to standardize a random variable X, which follows normal with mean mu and standard deviation sigma, into a standard normal variable Z, then you just do this X minus the mean and divide it by the standard deviation. So this is what we call a standardization step. Right? We remove the mean from, so this is nothing but this, we take this X from its original mean mu, and we shift it to 0 by minus this mu, and then by dividing this sigma divided by the sigma, that we kind of make the bell curve originally have a sigma standard deviation. Now we kind of shrink it or enlarge it depending on what the sigma is to put it into a standard deviation being 1. So that's what we mean by standardize this random variable. So yeah, like I said, why we would need this standard normal, because back in the days we have to calculate all these normal probabilities by hand. So standardizing the value and put them in a table, like a table, only one table for this standard normal distribution would be way easier comparing to do it for each mu and sigma pairs. So yeah, this is what it is for a standard normal distribution. Standard normal is just this normal distribution with mean 0 and standard deviation 1. And it's often called Z. And this is how you standardize a random variable. Okay, and the next is we have this thing called empirical rule for a standard normal distribution. So I said we have only one table for this standard normal. So everything is kind of fixed. Like for this Z, if we are trying to look for the z being, the probability of z being -1 and 1, which is one standard deviation away from the mean. So this range from the mean, it goes one standard deviation on the left and one standard deviation on the right. So this area under that bell curve is 0.68. So this is for standard normal. It will always be 0.68. And for two standard deviation, like again, this standard normal being -2 and 2, it would always be 0.95. But this is after like we rounded to 2 decimal places. And for 3 standard deviations away from the mean on both sides, the probability of this range would always be 0.997. Actually, if you go for another decimal places. So this means about 99.7% of the values are within 3 standard deviations of the mean. Okay, those are the values. This 0.95 is the most commonly used one. But this 0.99 is sometimes will be used. Well, this plot showing you what it means for this three equations here. So this is what we mean when we go one standard deviation away from the mean. Our mean is mu. Go one standard deviation on the left and one standard deviation on the right. And this area covered 68% of the data for this random variable. And 2 standard deviations, it covers 95% of the data. And the three standard deviation rate is 99.7%. Okay, so this is for standard normal. Yeah, we said the uniform is the simplest, and the normal distribution is the most popular one. And we have some other continuous distributions to cover, like exponential distribution. For this distribution family, the parameter is called a scale parameter, which is lambda. And the PDF looks like this. So from this, you can tell x can only be positive or positive or equal to 0. So this exponential function is often used when you model the waiting time between some events, like the amount of time between customer arriving at a shop or a phone calls come to a help center. And so when you try to model the data, you would have to have an idea like what the data would be like and what kind of distribution it could follow. So that's why like we have to study this kind of distributions to make sure you have these options to consider when you're trying to collect the data and study the data. So exponential function is like this with a scale or rate parameter, lambda, and it often trying to capture like waiting time between events. So, okay. Well, so for exponential distribution, it's a bit different from normal distribution where the mean and variance are just like single parameters. But here we only have this lambda involved in this PDF, and we actually know what is its mean and variance of this exponential family. And these are the formula given to you, so people have proved that the mean and variance is just some function of this lambda. So you will use this in some of your homework questions. And yeah, and oops. Both the mean and standard deviation of this distribution. Yeah, this is the variance. But if you talk about standard deviation, which is the square root of this, so mean and standard deviation are both 1 over lambda. What is this? I think this is about. Okay, yeah. Made another plot to show you what the exponential PDF for the exponential distribution looks like when we have different value of lambdas. So this lambda controls how steep this curve will go down. So when lambda equal to 0.5, it's just very slight, smooth curve going down. But when the lambda is bigger, then it goes down really fast. Like within 1 unit, it just goes from the PDF goes from 2 to like 0.25. And you notice this PDF can be over 1. It's not like probability. Probability of something is always within 0 and 1. But for PDF, so this function f for any of the families, it can be over 1.
Or exponential?
No, not for exponential only. So exponential can go over 1. Like normal distribution can also, like PDF can also be greater than 1. But for uniform distribution, you will not get anything over 1, right? Because the PDF
has to fall between the parameters.
Right.
Right.
Yeah. So this is the exponential distribution. Yeah. Okay, and the last one, I think this is the last one we are going to talk about, is beta distribution. So this beta distribution, it only have positive probability. Yeah, it only has positive probability for interval of finite length. So generally, it's always from 0 to 1. And also this beta distribution would have 2 parameters, alpha and beta. Yeah, I have this, but I didn't plot. But I didn't plot the curve for beta because it's kind of complicated. You can always go to like Wikipedia when you look for this beta distribution. It just have this 2 parameters controls the shape of a beta distribution. So I have this information here listed for you. Like if X is following a beta distribution with these 2 parameters, then X will only have positive probability from 0 to 1. And the mean and variance for this random variable would be like a function of alpha and beta. And these are just formulas for you to use when you're trying to find the mean and variance of this beta distributed variable. Well, I have to admit, like statistics is just full of these terms and things that you have to remember, you have to get yourself familiarized with. Well, the most interesting part for statistics is that once you have these tools and you have your data, you know what to think about when you look at your data. So we would have to use this information, use this knowledge. Now we go to R and see how do we do the calculations. Oops, yeah. This is all for the slides, and we will go to R and look at what we can do with R. And some of this would be very similar to your homework questions. But in the homework questions, you will have different scenario where you need to figure out what you are trying to calculate. So let me see. I hope this is big enough. Font. Is it? Can I just maybe I can enlarge it? No. I don't know. Let's see. Control plus. Yeah, that's what I did. But anyway, I'll do this. Okay. Yeah, so I listed the topics in this R markdown file. You do not need to know, but it's good to know what this R markdown is that you can like with certain formats, with all this, you can put the code and statements in one report. So this is a good way that when you're trying to make a report with your analysis, especially when you are working, it's better to make it neat and present your code and the results, the plots for either your coworker or your manager. So this is a great tool. And also I'm using this to show you some of the concepts in your lecture. So this is just a list of the topics we are going to talk about, like PDF, CDF for continuous random variables, and how do we compute like the probabilities, some of this. Let me see if I can read it directly. If not, well, it might take some time to install so many packages. But I'm thinking, yeah, I think I have this. So this is what it looks like once you meet this R markdown, and this is the report you will see, like with all the code and the results, the plots, and some of your like statements here. So let's just look at this for this is probably big enough.
Was that from the book?
No, this is just the R code that I trying to provide for you, so that you know where to find how to code it up when you work on the homeworks. I'm just using this like R markdown results just to show you the material here. Okay, so and also we will talk about how do we solve for this C and which satisfy this statement for a given Q, and how do we do the expected value, and yeah, this is basically what we talked about in our lecture, right? So let's work on some of the probability things in R when we have a uniform distribution. Say that X is a random variable of a measurement, and we assume this X follows a normal distribution with A equal to 0.5 and B equal to 2.5. And let's just plot the PDF of this X. So in order to do a plot, you would have to get two vectors in R. So one being the vector on x-axis, one being the value, the vector on the y-axis. So this is, I'm creating an x vector, which is a sequence of data with an increment of 0.01. That's from 0 to 3. And I get the D uniform, which is the density, which is the PDF for this uniform distribution. And I need to specify what is the mean and what is the max. So mean is the A value and the max is the B value. So this is how you get the PDF values corresponding to each of this X, right? And now you plot this X and the PDF to make this figure, right? And this is just how I choose what is the line, what is the type. I choose a line, and what is the label for Y axis, and for X axis, it's just by default, it's just put it here. And I named this plot like this. So yeah, this is just example. How do you do the PDF plot? Use R. And how do you do CDF? Again, you need this X vector to put on your X axis, and you need the Y vector, which is your CDF. Well, CDF you can get by this P unit. So this P unit is to get you the CDF for this X vector. And again, you specify this mean and max, the range for your uniform distribution, and you plot the CDF. Then you get it. But if I ask you what is the probability that X is less than 2 inches and less than 2 inches, which means I'm asking for this probability of X less than 2. And this is our CDF F2, right? That's the definition for CDF. This would just be F2. But when we're trying to look for this F2, we just put this 2 here, which is our small x value, and also specify the value for A and B, which is the range for this uniform distribution. You will get the probability. You will get this F2.
Will this be on Blackboard too?
Oh yeah, I have already posted this. Yeah, so this is how you get this F2, but if I ask you, what is the probability that X is greater than 1? So, which is this, Px greater than 1. So greater than is the opposite for the definition of CDF. So when we define the CDF, we define it X less or equal to a small x. So now I'm asking for this X greater than 1, then you just do 1 minus this, you get the other direction, the other area.
So ours default is to do the area that's less than, right?
Yeah, if you do this P unit, this is exactly doing the formula for this capital F, which is our CDF. So that's, yeah.
So that, yeah,
it's less or equal to.
Yeah, because the one that we did last time, we were supposed to do last time, also was, that's for the X is less than, right? The normal distribution and stuff.
Yeah,
like
yes. So this P, anything like with this P in front and any of the distribution names, it will just give you the PDF or CDF or CMF corresponding to the distribution. So like this is Px greater than 1, and you want to get the opposite direction, you do the 1 minus. So this is how you think about it. You first know what is the probability you are trying to get and translate it into the CDF thing. And next you can use this like R commands to do the calculation for you. So again, I'm asking what's the probability that X is within 25 inches of the mean measurement. So what is this asking? 25 inches of the mean, within 25 inches of the mean. So from the mean in the middle, so go left, 0.25, go right to 0.25. And we know the mean is 1. Oh, sorry. the
Okay.
mean. Yeah, so we have to calculate the mean as 1.5. And now we do this calculation. It's just this f of this value on the right minus the f value on the left. Because remember when we do the do this CDF thing. Yeah, when we do the CDF thing, it's you just remember this formula. You can do that. But if you like intuitively trying to get why it's like that, it's because we're trying to get the area in between these two values, and each of this capital F is doing the area on the left of this cutoff. So you have to get the like furthermost like one, which is this B. You get the whole area on its left, and then you minus the part that for this area on the left of this smaller value. So in that way, you get this area in between. The important thing is that you know this F is always the area on the left. So yeah, this is how you do the calculation for with R. And yeah, this is for normal distribution. Yeah, computing the normal in R. For standard normal random variable Z, let's compute the following thing, like Z greater or equal to 0 and less or equal to 1.3. So, which is just this P norm. Again, P norm is this capital F thing. So this is capital F 1.3 minus capital F 0. So this is, well, in this case, you didn't specify the mean value and the variance because it's a standard normal. This P norm by default, if you did not specify the mean and variance, then it's the standard normal. And again, for Z less or equal to negative 0.5, so we just directly do this P norm because this is just our CDF. It's a less or equal to. Yeah, Z greater than 3 is the opposite of the definition for CDF because it's greater than. We have to transform it back to less or equal to something, right? So that would be the opposite of less or equal to. So that's 1 minus. So when you're trying to get the opposite, you do 1 minus. Because when you sum them up, it's always 1, right? So
You can remember greater than 1.
no, when you sum up all the probabilities for this random variable, it's always just can be 1.
And it's only for the exponential that you can have it be greater than 1.
Oh, so that's a different concept. This is something very easy to get confused. So when you're trying to get the probability, so when we talk about probability, either a probability of a range or interval or a probability for a single value, it's always from 0 to 1. It will not, you will not get negative probability. You will never get like some probability being greater than 1. But when we talk about PDF, it's different. So PDF is when you look at those formulas, it could go over 1. Yeah, but for some of the PDF, like the uniform, it will not go over 1. But for some of the PDF, it can go over. Yeah. Yeah. Again, when we talk about probabilities, like this P of something, it won't be all
Because
of.
you can't have more than 100%.
Yeah, exactly. So for random variable X, following this normal with mean 2 and standard deviation 4. And how do you do a PDF for this random variable? And the same logic, you get this vector for X and you plot the x versus the corresponding PDF value. And you just pay attention when you specify the normal distribution, you need to provide the standard deviation, not the variance. Not the variance. You just need to give the standard deviation to this D norm, P norm, or anything for normal distribution. So this is how you do the PDF for normal distribution. And
So for normal, you basically said you have to make sure that it's the standard deviation, not the variance, basically, right?
yeah, so for this normal distribution, a better way to check if you don't remember, you can do this question mark. Let's just do D norm or any of this, like P norm, Q norm would also would just work. So because it's asking mean equal to something and this SD equal to something. So yeah, SD is the standard deviations. Sometimes you just forgot and you can always go check the help on R. Yeah, so same story here. Like this is just changed to a normal distribution, and you provide the mean value and the standard deviation. You get the corresponding probabilities. Yeah, I think you already know the trick for this one. So yeah, this is something new here. Let's use R to solve for the value C in this statement. So this psi, I think this is psi or phi.
It looks like
Phi, okay. Yeah, I sometimes got confused. So this phi C is the same as this P Z less or equal to C. So this is so this phi is a special character for standard normal. Like here Z is the standard normal, and we use this.
So if you see that anywhere, it's just going to be the standard normal of C.
Yeah, yeah. In statistics, that's the case. And we just use this phi for this standard normal to replace the capital F for like other distributions. So now we're trying to find the C value, like in this statement.
So this is finding the quartile normally.
Yeah, yes, we know the percentile or quantile. Yeah, we know the percentile, trying to find the corresponding quantile value C. So for this one, oh well, somehow it goes to it got centered. So we have these three things to work on. See, this is the first one, but it got to the center. So for this one, we know the probability, and we are trying to find the corresponding quantile. The probability is 0.45. And once we know the probability, we're trying to find a quantile, we would use this Q norm. So Q represents quantile. Previously, we used this P norm. Yeah, we mostly just use P norm, which is for the CDF. And Q norm is trying to find the quantile corresponding to this probability. So basically, it's trying to get the value C for this equation. And for this one, probability of Z less or equal to C equal to 0.99. And again, we notice this is the CDF for standard normal, right? It's a less or equal to. So we can just do this Q norm for this 0.99. We find the corresponding value C. But for this one, it's getting a bit tricky because this is the opposite of your CDF. this greater or equal to, you have to do 1 minus this probability, which is 0.01. Like 1 minus 0.99 is 0.01. And you trying to find the corresponding C for this probability 0.01. So this is the C for this statement. Well, I have put this another plot trying to interpret this in terms of a PDF. So I plotted the PDF for this standard normal, and this AD line is just put a line at 0 when fx equal to 0. So, and this AD line B is a vertical line, so put on the plot. So this is a vertical line at Q norm 0.45, which is this blue one. Yeah.
What is the LTY?
Oh, this is the line type.
Oh.
So I chose two corresponding to like dashed line.
Oh,
and this are the colors. Yeah, and if you look at this one, Q norm 0.45, where we know this 0.45 is the, look at this, is this P, Z less or equal to C equal to 0.45. So this is the area under the bell curve on the left of C. So this is the corresponding C value. See, this Q norm will get you the C value already. So this 0.45 is just the area under this curve, but on the left of this blue line. So it's very close to 0.5 because see, this blue line is very close to the center of the bell curve. And the whole area under this bell curve will always be 1. So this Q norm 0.01 is the probability of following the area on the left of this green line is 0.01. So you can tell it's really on the far left of this curve, and the values in this area is really like, you only got a very small range of the value for this random variable. And for this 0.99 and this red line, where the probability of following this on the left of this red line is 0.99, and you see a majority of the values are on the left of this red line. So, okay, that's for the normal distribution, and we have this for exponential distribution. So for exponential, we would have this D exp or P exp, Q exp. It's the same thing, just as previously, but we are changing to a different distribution. So again, this exponential is measuring like timing between events. So this example, like suppose I run a coffee shop and X denotes the time between new customers arriving. So in a long experience of running this shop, I have to collect enough data, and I find the parameter for this exponential distribution is 1. Suppose an order takes about 2 minutes to take or make. What is the probability that another customer will walk in before the order is done? Within 2 minutes without a customer. So that's asking what's the probability of the waiting time less or equal to 2. So this is just corresponding to the PDF, sorry, CDF. you do this PEXP, you give this value to here, and now you have to specify the rate, the parameter for exponential distribution. Now it's the rate. So lambda equal to 1. And what's the probability that there is more than 5 minutes between customers coming in? More than 5 minutes for like arriving time. So that's x greater than 5. So when you see greater than, it's the opposite of less or equal to, where the less or equal to corresponding to our CDF. So that's what we can get from this PEXP. So yeah, this is something very easy to forget. You do the 1 minus. So what is the value x star such that we expect 95% of times to be less than that time? To be less than this x star time. Now we know the probability, like being 0.95. Now we're trying to find this x star. So whenever you see, you know the probability, you're trying to find the value, the quantile, you do QEXP. Q is the quantile. And again, you have to specify the lambda value. Yeah, so this is another example to show you how to get the PDF for exponential distribution. This lambda equal to 1, and this is corresponding CDF. Yeah. So yeah, CDF. When you look at the CDF, it's I mentioned that the value of probability would never go beyond 1. Actually, the area under the curve, the PDF curve, will not go over 1. If you look at CDF or many, we have this, it's just kind of converged to 1 when you go to the limit of the values that x can take. So CDF would never exceed 1. And this is just a very short example for beta family. And I think I probably forgot to mention the beta family are mostly common for modeling proportion, probability, like some kind of rate. It's very common to use in like IT company for data scientists or data analysts. When you work on like click-through rate or this rate thing, a proportion thing, you would need to use this beta family distribution. And these are the commands, for this beta distribution. Let's look at the question. Suppose the proportion of voters in a zip code that support a certain policy is suspected to have a standard beta distribution with alpha and beta values like this. It's asking what is the probability that more than 50%, so the proportion being 0.5, more than 50% of people support a policy. So it's asking the probability of p greater than 0.5. See, now I use this random variable being p because it's normally just working on some proportion, some probability thing for beta. So this p is following beta, alpha equal to 2.5, and beta equal to 4.5. So this is how you do the calculation. So once you know those tricks, it's pretty simple. But just remembering like all these distributions is a pain. But once you like work more and more on this, you will get yourself familiarized. Yeah, and this is actually all the material for chapter 4. For our class, there are way more distributions or families that you can look. But I would say many of them are not very commonly used. But the ones that we covered here, and also for the discrete distributions, maybe only just a couple you will use. Even you work in industry as a data analyst.
So usually you can tell which family to use if like you're not looking at what's given to you by the wording. Like if you see something that's using proportion, it's more likely to be beta. If you see something using like time between, it's probably
yes. Right. Yeah, I think that's it. Oh, and did I mention that the homework 4 is up? Yeah, on level 7. So yeah, again, if you have any questions, either ask our TA. TA has plenty of office hour times. And we also have office hour, and also like you're welcome to send email asking me question. Like discussion board, I saw questions on discussion board, but like later date, not immediately. I find, oh, there is a question. But if you want to get sooner help, the best way, contact me through email. Come to office hour, my office hour, or TA office hour. Yeah, I guess that's it for today.